have here a balloon in my car. It's a helium balloon. That's why it's staying up by itself. To be honest, I'm not overly a fan of helium balloons. It's a great wastage of a resource that we are running out of. We are running out of helium, and it's much better used for more important things like MRI scanners, etc. However, when your little girl goes to a birthday party and comes home with a helium balloon, well, we're not going to waste that, are we? No, we're going to make another science video. So I'm just sitting in my car, it's parked, and I'm just going to drive off. Now, the question before I do that is, what do you think might actually happen? Because, of course, according to Newton's laws, the balloon is an object at rest, and when the car moves forward, well, the balloon's not bolted to the car, so it should stay an object at rest, and therefore it will appear that the balloon will move towards the back of the car. Let's have a look. Okay, I hardly even moved then, actually. Stop moving. I hardly even moved the car, and the balloon did its thing already. It didn't move towards the back of the car. It actually moved forward. Now, it's a bit of a hard thing possibly for you to notice, because the angle of the camera, but the camera's just sitting in front of my stereo so that I can drive. So the balloon has actually moved forward when I moved the car. Came towards my phone, and hopefully you saw it get bigger. Let's do that again. Yeah, it definitely moved forward. Now, here's another thing. I'm about to turn the corner to the left. Watch what the balloon does. The balloon moved to the left. Now there's another corner coming up, around to the right. And check out the balloon's response. It moves closer to me, over on the right. So that doesn't really seem to follow Newton's laws at first glance. Now when I put the brake on, the balloon moves to the back. That doesn't really seem to follow Newton's laws of motion. And they are laws of motion, they're not ideas. These things are actually legit. Objects will remain in constant motion unless acted on by an outside resultant force. That's Newton's first law of motion. Now you note this when you stand on a bus, and maybe there are no seats left, so you're standing up and then the bus moves forward and you sort of stumble backwards and try and catch your balance again. Or if the bus moves to the right, you fall onto the people to the left of you. That's because you were an object in motion and you stayed an object in the same motion even when the bus started moving or turned out from underneath you. That's why we wear seatbelts. Because if the car stops suddenly, well, you weren't bolted to the car, so you don't stop suddenly and you keep moving forward, and that's what we call flying through the windscreen. Not pleasant. But the balloon did the opposite. I'll put the car in reverse. I'll just go a little bit back, and the balloon moves to the back of the car. And if I put the car in first, when I move forward just a little bit, the balloon moved forward. Silly balloon, that's not what it's meant to do. Not according to Newton's laws. When I moved forward, the balloon should have appeared to fall backwards. When I turned the corner to the left, the balloon should have appeared to fall to the right, like you on a bus. When I moved to the right, it should have gone off to the left of the car. The balloon did the opposite. So what's going on here? Alrighty, here's a balloon filled with helium. Hence it's an up balloon, or a sky balloon as Peppa Pig might call it. Now I'm sitting in the car and I'm about to drive off. Let's see what happens to the balloon. Think of what happens when you're standing on a bus and the bus takes off, you fall to the back, don't you? That's from Newton's laws of motion, the first law of motion. An object will remain at rest unless acted on by a resultant force. So when the bus accelerates forward, well, you didn't accelerate forward, so you actually stay where you are, but with the bus moving out from underneath you, it appears like you fell backwards. So let's take a look at what the balloon does. Now hold up. Did we just break physics? Silly balloon moved forward. What's it doing moving forward? I drove forward. The balloon should have gone to the back. Alright, let's try that again. I've put the car in reverse. And let's watch the balloon now fall towards the front of the car. Wait, it didn't! Did we break physics again? The balloon moved to the back of the car. What is going on? Let's drive forward again. And the balloon moved to the front. Okay. Let's just drive up the road a little bit. There's a decent corner coming up shortly. Alright, corner's coming up. So, I'm about to turn left around the corner. Now, just when the bus turns left, you fall off to the right. Okay, so the balloon should come to the right and hit me. Here I am. Should hit me in the face. Let's go around to the left. Hold up, the balloon didn't go to the right. It went to the... Now I'm about to turn right. Here's another corner, turn right. And now it did hit me in the face. What's going on, Mr. Balloon? Well, what's going on indeed, Mr. Balloon? Let's talk about that first law of motion, Newton's first law of motion. So, I mentioned, pen will work, there we go, better. Here's the bus, you're standing on the bus, here's you on the bus, and when the bus, let's give it a front window, there we go, now we know which way it's going to go this way. When the bus moves forward, you appear to fall backwards on the bus. So, from your point of view, it's as if you did this. You fell back. That's actually not what actually happened. What actually happened was you stay in pretty much the same place. The bus, on the other hand, accelerated forward. So you can see that you actually stayed in the same place because there wasn't a force accelerating you. You're an object at rest. You stay an object at rest. The bus just accelerated out from underneath you, so it appears like you fell towards the back of the bus. Okay? Right, so let's talk about the balloon. It was a helium balloon. It was floating up. That was really bad drawing. Let's try that one again. Here we go. Here's your balloon. There we go. It was floating in the car. And because it was helium balloon, here we go, had some helium in it, and then I drove forward. Now the car moved this way. According to Newton's law, it should appear, according to the first law, it should appear that the balloon would fall towards the back of the car because the car accelerates but the balloon stays where it is. So the back of the car catches up to the balloon, makes it look like the balloon went to the back of the car. Not actually the case though, the balloon actually went forward. When the car went forward, the balloon also went forward. So we broke physics, except no, we did not break physics. You can't break physics. So what's actually going on? Well, the balloon, remember, was an up balloon, right? It was filled with helium. It was buoyant in the air, so it was rising to the top, right? It was less dense than the air. It was rising to the top. It was buoyant. It was floating upwards. Now, when the car moved forward, let's draw another diagram. Let's draw a car. Here we go. It's a car. There we go, and here's our balloon in the car. Lovely. So, when the car moved forward, the air in the car actually got a bit squashed up towards the back because suddenly the back window starts moving forward and pushing all the air molecules together. So, before the car was moving, we had these air molecules in the car nicely spread out, nice and even, because it's just sitting there in the car. But when the car moved forward, this happens. So the car goes this way, and now the back window moves to the right. And so what it's actually doing is squashing up the air molecules at the back of the car, making higher pressure compared to the front of the car. Okay, so remember, it's all compared to. We're not saying, yeah, the pressure was really, really high. What we're saying is the pressure of the air molecules at the back of the car was greater than the pressure of the air molecules at the front of the car. And this is why the balloon was actually pushed towards the front of the car. Of course, there's a force that pushes from high pressure to low pressure, right? That's how airplanes work, isn't it? Let's draw an airplane wing. Well, again, not so good with the diagrams today. Oh, okay, third time lucky. Let's go like that, and then we'll go like that. There we go. So there's a much better shape of an airplane foil, an airplane wing. Right, so the airplane moves forward. Here it goes. Some air has to come underneath the wing and some air has to go over the top of the wing. But of course, we can't create a vacuum at the back of the upper surface of the wing, so they have to meet up at the end. Now, the air moving over the top of the wing actually has further to go than the air moving under the wing, just simply because of the shape of the wing. It's a longer path over the top. So this creates a low pressure with respect to the air under the wing, which is high pressure. Okay, because the air molecules going over the top, because they've got further to go, they get more spread out, so we've got a low pressure. And of course, there's a force of from high pressure to low pressure, so the wing is pushed up, and the rest of the plane, being bolted to the wing, moves up with the wing. Grand. So we've got this force pushing from high pressure to low pressure. Okay, the balloon was just floating upwards because it was buoyant in the air, but now it's going to float to the right even though the car is moving to the right, because it's less dense, it's more buoyant than the air at the back of the car, so it moves to the front of the car. Hopefully this is all making sense. When I put the brake on, let's get rid of some of these. When I put the brake, actually let's talk about when I reversed. When I reversed, so come on pen, do your thing. There we go. Okay, car moving this way now. Well, now the same thing happened, but at the front of the car. The windscreen was bunching up the air as it was backing onto the air molecules in the car. It was bunching them all up, making high pressure at the front of the car now with respect to the air molecules at the back of the car. So, of course, the balloon was buoyant towards the lower pressure. It moved to the back. Even though the car was moving to the left in this diagram, the balloon also moved to the left. So we didn't actually break physics, we actually used physics. It's all about the density of the air molecules and the buoyancy of the balloon. Similar when, new diagram, how do I draw a car from above? Okay, there's a tire, there we go, 4 tires, windscreen, great. And the balloon was floating in the car. When the car turned to the right, Newton's law of motion, the first law, would suggest that the balloon would fall back towards the left, but actually it moved to the right. It's all the same principle. When the car moved to the right, the left-hand side of the car was bunching up these air molecules, bunching compared to the few spread out air molecules over the side. So we had a pressure, a force pressure moving from the left of the car to the right. So the balloon moved to the right and smacked me in the face. Here I am getting smacked in the face. Sad. Actually, not sad because it was a balloon. It didn't hurt. There we go. So we didn't break physics at all, but it's good fun to play with a helium balloon. Well, let me rephrase. It's good fun to play with a helium balloon that one of your year 10s left in the science staff room. Of course, we would never go and get a helium balloon because that's a waste of helium. We're not even getting into that today.